Aloha biostatisticians. I'm recording this video for you today because I want to help you walk through the lab for t-test step by step. I made some changes from last time, so now it should work very smoothly. I'm sending you a folder. That folder contains 3 files, 2 notebook files, and the data. Download that entire folder. This is what it looks like. There's the notebook, two-way t-test comparing pulse means, and the notebook graphs 1. And here's the class data. As long as they're all in the same folder, everything should be just fine. Open up the two-way t-test comparing pulse means. And you can see it looks the same at the beginning. We already did this together in class. So fill in your question, your null and alternative hypotheses. We already collected the data. Now we can focus on the analysis. This says to download the class data as a CSV file, but you don't have to do that. I did that for you already. You can just run this chunk. A chunk is anything between this little dash, 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 curly brackets R, curly brackets, and I put some other labels in here, and this dot, dot, dot. It's highlighted, it's grayed out. That's a chunk, that's the code. To run it, just go over to the right and hit the little green play button, run current chunk. It runs everything in that chunk. And as soon as I did that, you see it pops up here, class data, 23 observations of 12 variables. And if you click the blue arrow, you can see here are all our data, and you can see that before pulse and after pulse read in as numeric variables, which is good. That's what we want. We didn't have to specify the pathway. We didn't have to do anything but run this library read R and say class data, read CSV, class data CSV. It knows where to look as long as the data are in the same folder as the notebook. I included some other steps in here that you may or may not need to use for doing your homework. This is the data wrangling part. First, we're going to take a subset of the data that includes only the variables of interest. Keep an eye in the upper right-hand corner here. You'll see it appear. So if I run this chunk here to create pulse data frame, which is going to be a subset of the class data that includes only before pulse and after pulse, run this chunk and look, pulse data frame shows up. I click here and I can see I have before pulse, after pulse, all these nice numbers. We have 23 observations of 2 variables. Great. Come back over here to the tab for your notebook, and we'll remove any missing values or NAs if necessary. I think we didn't have any, but I want to include this in here in case when you're running your own data for your homework, you need to do this. You have the code. Run this chunk, and it works just fine. Now, if R reads in your data as a character, which it often does if there are any missing values, you have to change the data type to numeric. Here's how you do it. You run this chunk, you see where it says the function as numeric, the column that you want inside the data frame, and store it into the column that you want to call it inside the data frame. Do this for both before and after. Run this chunk. Nothing's going to change. It was already numeric. Then to do a quick summary on the data, run the next chunk. All this does is summary. Pulse before, pulse after. after pulse, before pulse. And it gives you this output here. This is the output for before pulse, and below it is the output for after pulse. It includes our minimum, first quartile, median, mean, third quartile, and maximum. Right? So our minimum value is 56, first quartile 60, which means 25% of the people have a pulse 60 or less. Median, if we lined everybody up from the lowest pulse to the highest pulse and we put that person in the middle, their pulse would be 68. Mean, that's just our average pulse for the class before we do exercise. Third quartile is 80. That means 75% of the people have a pulse less than 80 and 25 greater than 80, and our maximum is 88. For the after pulse data, again, our minimum was 72, first quartile 84, median 88, mean 87, third quartile 92, max 96. And I just want to point out real quick with these data, you can see that the median here is 68 for the before, and the mean was 72. Those numbers are pretty close, but they're a little bit different. And that often indicates that our data are skewed. Whereas for the after data, the median is 88 and the mean is 87. That's really darn close. That's less than one different. So that means our data are probably very normal when the mean and median are in the same place. There's a lot more to look at with the data that starts to give us an indication about the nature of our data. Real basic, simple summary statistics. Summary statistics. Okay, now we need to check our observation. First, we want to check that the data are a simple, random, or unbiased sample, SRS, simple random sample from the population. So how do we define our population? If we define our population as students at UH, then is there any reason to think that the students that sign up for the biostats class have resting or after pulse rates that are different than the rest of the student population at UH? I can't see why. What if we define our population as students in Hawaii or college students in Hawaii? Maybe we should say college students, because maybe elementary school students would be different. So maybe we define our population as college students. And are the college students in Hawaii maybe different than the college students in another place? Maybe, I don't know, but I think it's fair enough to assume that our sample is a simple random sample. It's not biased in any systematic way that would influence our results that I know of. But if you think of something, let me know. The data are numeric. Yes, check. Our data are numeric. We took a measurement. We've got numeric data. For your homework, you need to have numeric data. You've got a categorical variable, right? You've got the two categories, in this case, before and after, before pulse and after. And then you have a number. You measure something. When you're thinking about doing your homework, make sure that you're measuring something, or at least it could be a count like your number of heartbeats, but it's got to be a count that includes a wide enough range. If you roll a die, for example, if you just roll one die over and over, the data range is going to be 1 through 6. That's a pretty small range. That would be considered a discrete numeric variable. Don't do that. That'll mess it up. You want a continuous numeric variable where theoretically your data could take on any number, and not categorical variable, right? If it was before hair color and after hair color, no, that doesn't work. Numeric data. The observations are independent. Now, this is a tricky one because we're doing a paired t-test. So really our observations are not entirely independent. You might imagine that the pulse rate for a person before might have an influence on their pulse rate after, right? A person with a really low pulse to begin might have a low pulse after, or high pulse to begin, high pulse after, right? They co-vary in a systematic way. The before and after co-vary in a systematic way. They're paired, they're related to each other. right? If we had taken a measurement of 23 people resting pulse before and a separate 23 people after exercise, those data would not be paired. Those are independent completely. But we can say our data are independent observations in the sense that the pulse rate before and after of any individual student probably doesn't influence the pulse rate measurement of another student, unless just being next to each other is like really exciting and it kind of gets your pulse up. You're like, oh my God, that's so exciting. We're together. The population is normally distributed. Now, we don't know anything about the population. We've just got our sample. We have to make inferences about the population from the sample. But that's usually fair enough to do. Usually, if we take a simple random sample of a large enough size, it should represent the population reasonably well. So we can look at the distribution of our sample to see if it's normally distributed. And here's step one to do that. Make some histograms. Easy, right? I already started doing this and it saved it, but I'll show you how it looks to do it from scratch. So it's just this hist. Hist is the function name. And inside hist, you just put the variable of interest. Again, you want to say, look inside the pulse data frame. The $sign says in the column called before pulse. And here I added the command breaks equals 5. So the breaks are every 5 heartbeats, which seemed like a good number to me. I wanted them to be the same, so I specified that. Otherwise, if you leave it blank, R just comes up with a break that it thinks is good. That's fine. And I'm going to store it into something called H1. And then we'll make another histogram of after breaks 5, store that in an object called hist2. If you run this whole chunk here, hit the green play button, bink, you get 2 histograms. You can toggle back and forth between them. Again, notice that the graphs show up in line. Before, when we were running scripts, our graphs showed up in the bottom right-hand corner, but now they show up in line and they'll print out into a nice report for us that way. So, looking at this. Okay, let's look at this histogram. So, the histogram before, again, our range 55 to 90. We definitely see a strong right skew. We have a lot of people with a pretty low pulse rate, probably because we have a lot of young, healthy people. Good. I'm older and I think my pulse rate was still pretty low. So that's a good thing. And then a few people have higher pulse rates, nothing too extreme. And our histogram of after pulse looks a little more normal. I really like how this just happened to have turned out where we have these 2 variables. One turns out to be not quite normal and the other one is normal. And I think that's going to be really useful for you to be able to see what not normal and normal data look like side by side. If we overlap the 2 histograms, run this next chunk here, you have to go in order. If you skip something, it won't work. Go back and make sure you ran everything. Then you see in blue, there's our before pulse. In pink, there's our after pulse. Again, the before was right skewed. The after is nicely bell-shaped and symmetrical. It's very normal. And something else we might notice from this is that they're not totally overlapping. They seem to be different. The centers are different. The measures of central tendency are different probably too, right? We saw different means and different medians. And we can also see here that the spread of the data are fairly similar between these 2 variables. The amount of variance is similar. Now, we're not going to assume equal variances. We don't have to do that, but it's nice to see that they're not radically different. One isn't extremely narrow, one's not extremely wide, which helps to make the t-test more valid, given that our data are not quite normal. Another way to check for normality is to look at QQ plots. Very good idea to look at QQ plots. So to look at the QQ normal plot and to plot a QQ line on both variables here. We just run this chunk, and again, we can toggle back and forth between the two graphs. Here's our normal QQ plot before pulse, and you can see, so this line here is where you would expect the points to fall if the data were perfectly normal. And the points are the actual data. So you can see that the points don't quite fall on that line. Again, this is not quite normal data. It's right skewed, and you can see that because the points are not falling on the line. Interesting. They're not super far off, but they're not on. And if you look at the after pulse, now you can see, oh, look, the points are falling a lot closer to the line. So this is what normal data look like. Not normal, normal, right? Isn't this helpful to see that right side by side? Another thing we can do to check for normality is hypothesis test. The t-test is a hypothesis test, but there's like the hypothesis test that you do before the hypothesis test. There's a few different versions. Here we're going to use the Shapiro-Wilk test to test for normality. To do that, we run the function Shapiro.test on our before pulse and Shapiro test on our after pulse. Hit the play button to run current chunk, and we get these results down here. Shapiro-Wilk normality test. Yes, that's what we said to do. The data, pulse data before pulse, right? The test statistic in this case is a W. I guess it's a Wilk. And it's 0.91022. And the p-value here is 0.04, which is less than 0.05. At an alpha value cutoff of 0.05, we reject the null hypothesis, and that means our data are not normal. Right? Skewed. They're right skewed. We saw that in the histogram, we saw that in the QQ plot, and we see that here in the normality test. It's pretty good confirmation. They're not that far off. The p-value here is not that far off from 0.05. But if we wanted to be strict about it, we'd say, okay, they're not normal. Then if we look down here for the after pulse results, the p-value here is greater than 0.05, which means we don't reject the null hypothesis, which means our data are normal. Now, let's get this straight because students get confused about this all the time. It's a little bit tricky. Just remember, for the normality test, if the p-value is less than 0.05, the data are not normal. Remember our before pulse, not normal, less than 0.05. If the p-value is greater than 0.05, like our after pulse data, the data are normal. Keep this example in your head for later. Next, we can run the t-test. Now, I'm saying here that the data look okay. I know that it's not quite normal, but remember the t-test is robust to deviations from normality, so we're going to go with it. So to run the t-test, and I've given you this code so you can use it for your homework. The function here is t.test. If you want to know more about this function, you can either run $t.test, or you can look down here in the bottom right-hand corner. There's a built-in help menu in RStudio, and you can search for anything. Here I search for the t-test, which is in the basic stats package. And down here, it shows you how to use that function. First of all, it shows you the function and what you input into the function, the parameters. And it shows you the default. The default is to have an X and a null Y. In this case, we have an X and a Y. It also has a default of running 3 different versions of the test: two-sided, less than, and greater than, both the two-sided and 2 versions of the one-sided test. Also that mu is equal to 0, paired equals false, equal variances equals false. These are the defaults, and confidence level 0.95, 95% confidence interval. There are other ways of running it. There's a formula version of the t-test that you can use. We'll see that later. And it shows you what each one of the arguments mean. X, Y, alternative, right? It walks you through step by step how to understand exactly what's in here, what the results mean. And there are some examples, and you can even run those examples right here. Or you could plug in your own data. You can copy and paste these examples and then plug in your own data. So if you're not sure how to run the t-test, there's a help menu right there. You can use the code I gave you. You can use ChatGPT. You got this. You got so much help. Everybody's on your side here. All right. We're going to do this t-test on our pulse after as the X variable. Notice I put the pulse after as the X because it's going to subtract the Y from the X. And if we subtract our after from our before, you know, if we have like before minus after, we're going to get a negative value, and that's just a little less intuitive to work with. So I put after minus before. That way we have positive values to work with. So pulse after, comma, pulse before, there's our X, there's our Y, and here I specified alternative two-sided. Yes, I know we talked about this is a one-sided test, but when I ran the one-sided test, I got a weird error message. I wasn't sure what to do with it, so I just went with the two-sided test. The results come out essentially the same. Paired equals true. The default for R is that paired equals false. Come back over here to the help menu, and it shows us that the t-test default is paired equals false. So you have to specify paired equals true. If when you do your homework, your data are not paired, you can either delete this little bit here. Be sure to delete the comma too. You can take that out, or you can change this true to an F or false. If your data are not paired, you change that part of the code. If you have questions when it comes time to do your coding, ask us. Here I also specify variance equals false. This is saying do not assume the variances are equal. I don't really have to put that in because that's the default. I just added that so that you can see we're not making that assumption. This code runs that whole test and then stores the results in this object called tResult. Then to see the results, we run tResult. Or run the whole thing at once by hitting the play button to run the current chunk, and we get our output right here. And it starts by saying data, pulse data frame after pulse, and pulse data frame before pulse. Those are our input variables. That's what we told it to do. Great. The test statistic, which is in this case a T. Remember for the other test, it was a W. It's different for a different test. But the t-test has P as the test statistic. Could have known. Right. The test statistic here is 10.112. The degrees of freedom is 22, and the p-value is wicked small. It's wicked small. It's 9.85 e to the negative 10. So it's like 0.00000000000. Did I get enough zeros? All those zeros, 9, right? It's a lot less than 0.05. That's all you need to know. And we have here our 95% confidence interval for the difference between the means and the mean difference. The mean difference here is 17, and the confidence interval is 13.5 to 20.4, which means that the difference between the means of before pulse and after pulse is 17. So if you take the mean of before and the mean of after, and you subtract before from after, you get 17. And the confidence intervals, the brackets around them, we were like, we're not exactly sure what the population is, but based on the sample, we would expect that the whole population true mean is somewhere in between 13.5 and 20.5 if we round it, right? The true mean is somewhere between 95% of the time that you do this same experiment, the true population mean is going to be between 13.5 and 20.5. And that means that 5% of the time that you do this, it's going to fall out. It's not going to be in those brackets, but we're okay with that. Close enough. And we think that it's centered at 17 because based on our data, if it represents the population accurately, the mean is 17, somewhere between 13.5 and 20.5. All right, you got that? Let's go on to a non-parametric test, which we will talk about more later, but I want to give you the code for it here. If our data do not meet the assumptions of the t-test, we have these non-parametric options. These do not assume normality. They don't assume normality, so they're a little more flexible. The non-parametric equivalent of the t-test for two related samples, matched samples, in other words, the paired t-test in a non-parametric version is the Wilcoxon signed rank test. Yeah, that's a mouthful. Here's more information on it. Here you can follow this link to read more about it. And down here, we can run this chunk to do the Wilcox test. You can see the code syntax is very similar. Wilcox test instead of t-test. Oh, let me just change this to after pulse, before pulse. Yeah, I will send you the version that I actually am running here. All right. Warning, cannot compute exact p-values with ties. We have some ties because this is a ranked test. That's okay. Little red, don't freak out. And we get here a test statistic, that's a V of 276. Our p-value again is vanishingly small. Not quite as small. It's a somewhat less powerful test, you might say, but it's still much less than 0.05. And our alternative hypothesis is that the true location shift is not equal to 0. We're not comparing means anymore with the non-parametric test. We're comparing ranks. It's a little different. We'll talk about it in the next few weeks. Now, if our data are not paired, if you do your homework, you can't meet the assumptions of normality, you want to run the non-parametric test, your data are not paired, here's the code right here. You just don't say paired equals true. It's the same function, Wilcox test, X, comma, Y, run the code. And in this case, you get the same answer, really. You get a W as is 40 instead of a V equals 276. But again, your p-value is really small, saying, yeah, there really is a difference. There's a big difference. All of these tests say that there's a difference between before and after. Now we come down to interpreting the results. What is the difference between the two means? Well, remember in our output for the t-test, it told us right here, the difference between the means is 17. Type that in. What is the 95% confidence interval? Again, go to the paired t-test results and you see the 95% confidence interval, 13.5, 20.5. Just type that in. Does the 95% confidence interval contain the mean difference? Is 17 somewhere between 13.5 and 20.5? Yes. Yes, that means there's a significant difference. What is the p-value? Now, you don't have to type out all that. You can just say it's less than 0.05. Here, let me type everything in here. So the difference between the means is 17. The 95% confidence interval, we can just copy and paste it from up here. 13.5, 20.5. Does the 95% confidence interval contain the mean difference? Yes, right? 17 is somewhere between 13.5 and 20.5. What is the p-value? We don't have to write out the whole p-value. We can just say it's less than 0.001. Less than 0.001. Can we reject the null hypothesis? Yes, we reject the null hypothesis. Remember, the null is that the difference between the means is zero. Is the mean zero? No. The difference between the means is not equal to zero. The difference between the means is 17, somewhere between 13.5 and 20.5, right? Not zero, far from zero. 13.5 is a long way from zero. So we reject the null hypothesis. There is a difference between the means. Do the non-parametric test change our results? No. We get the same result either way. We find out there is a difference between the means. Reject the null hypothesis. There's a difference between the means. Well, correction. For the non-parametric test, we're not testing the means anymore, but there's a difference between the variables. What did we learn about pulse rate and exercise? Well, what did we learn? This is up to you. You could say, well, we learned that pulse rate increases with exercise by about 17, which is some percent of the mean. Or we could say something like our mean pulse rate before exercise was significantly lower than our mean pulse rate after doing 10 jumping jacks, or our mean resting heart rate, BPM, the units there, is significantly lower than our pulse rate, BPM, after doing 10 jumping jacks. Oh, maybe I should type that there for you. Our mean, instead of pulse rate, let's be more biomedical about this. Resting heart rate is what you would say in medicine, right? Our resting heart rate in BPM, beats per minute, is significant. You know what, let's not say significantly, because if it's different, it's different. If it's significantly different, it's different. If it's not significantly different, it's not different. So it's just different or not different. Let's say is 17 beats per minute lower, and then we can put, let's say, then our heart rate after doing 10 jumping jacks. Wait, we need to put our confidence interval in there somewhere. Mean resting heart rate is 17. Okay, let's do that cool plus or minus. Let's see, 17. And then we need to say, what's the difference between 17 and 20.4? That's 20.5, 3.5, right? Yeah, either way, it's 3.5. So plus or minus, our mean resting heart rate in beats per minute is 17 BPM plus or minus 3.5 BPM, 95% CI, lower than our heart rate after doing 10 jumping jacks. Open up your parentheses, put your T, your P, T, comma, DF, P. What are they again? Let's go look at them. Where did we get that? Up here. DF was 22. T was 10.1. You don't have to type all the numbers. You can round. T, 10.1. Degrees of freedom equal to 22. P, you don't type in that whole number. Just put is less than 0.001. period, our mean resting heart rate in beats per minute is 17 beats per minute, plus or minus 3.5 beats per minute, 95% confidence interval. Let's put the 95% confidence interval after BPM. That's more elegant. Lower than our heart rate after doing 10 jumping jacks. Notice I didn't just say it was different. I said which way it's different. It's lower than, right? And I said how much it's lower. And I put the confidence intervals around there so you know, oh, it's, plus or minus this much. It gives you an idea of the variability. It's pretty tight. That's pretty good. And then my supporting evidence to say that there's a difference, my t-value, my degrees of freedom, and my p-value. And when you look at this, you can say, okay, that's a pretty big T. Degrees of freedom 22. Oh, I already know that I've got 23 observations then. And the p-value is real small. Okay, that's a difference. I don't have to say significant difference. I put the p-value and the reader understands that it's a significant difference. If I say it's different, it's different. If it's significantly different, it's different. If it's not significantly different, it's not different. So don't even say that. Just say it's not different. Okay, what other questions can we ask about pulse rate and exercise? A lot of things. You could ask a lot of questions about this. This is actually hugely important for our health, and a lot of you are pre-med, so think about it. Write something, then knit the notebook. If you were able to run all these chunks, then you're able to knit the notebook. I was actually able to knit it before I did anything. I knit it right away. So just come up to the top here. You see this little ball of yarn and then the knitting needles. Does anybody here knit? I don't knit. My grandma knits, so it's cool, but I don't knit. She makes really cool like Afghans and stuff. She's always like, you want an Afghan? I'm like, Grandma, it's not cold where I live. Okay, drop down menu, knit to HTML. If you try to knit to PDF or to Word, you'll be prompted to install other packages, which you can, but for now, keep it simple, knit to HTML. Knit to HTML, and it runs it. You see it running down here. And for me, this pops up. Now you should have this filled in with your question, your null, and alternative hypotheses. All your analysis, your graphs show up right here. Just like this. Interpretation of the results. That's it. And where is that file? That's the file you want to submit. Go back to that folder that contains the notebooks and the data, and boom, there it is. Now I'm using Chrome as default, so it shows up with the Chrome symbol. If you've got a different web browser, it might show up with a different browser symbol, but it's an HTML document. That's what you submit to LaLima. Right. Next, assuming all that worked, open up the Graphs 1 notebook.